Hello, and welcome to Algebra 2 with Trigonometry. My name is Kirk Weiler, and what I'm going to be doing in this video is giving you a little lecture to walk you through really the basics of introductory trigonometry. This roughly corresponds to the first portions of the first unit that we teach at Arlington High School on trigonometry in Algebra 2 with Trig. So let's jump into it. I want you to keep in mind that this doesn't correspond to any particular lesson or worksheet or anything like that. I'm just going to be walking you through the basics. So let's do it. Alright, well, before we really get into trig whatsoever, I'd like to talk a little bit about angles. Alright, and we're going to only think about angles right now in terms of degrees. Now, when we think about trigonometry, what we always want to do is we always want to measure an angle from sort of due east, from the positive x-axis, alright? Angles that are counterclockwise will be thought to be positive angles, and angles that are clockwise will be thought to be negative angles, all right? Because an angle is a rotation. It's not just the space in the V, but it's actually a rotation. So if we rotate counterclockwise, that's a positive rotation, and if we rotate clockwise, that's a negative rotation. But always think about the initial ray of the angle, right? Every angle has an initial ray and a terminal ray. Whoops. And a terminal ray. That almost looks like the word terminal. Not really. But that initial ray is always pointing along the x-axis, and the terminal ray, well, that's pointing somewhere else. Okay? So we talk about angles. Now, what we're also going to be talking about are what are called reference angles. All right? Now, every angle has a reference angle. And the reference angle is simply the angle that the terminal ray makes with the x-axis. Now you might say to yourself, well, I thought that was just the angle. All right, but the reference angle is always an angle that's somewhere between 0 degrees and 90 degrees. It's always between 0 and 90. So for instance, let's say I had my initial ray, and again, let me put a little dashed line there for the whole x-axis, and let's say that I came over here, right? So that my angle was, I don't know, let's say 160 degrees. All right, its reference angle then would be this thing. That would be its reference angle. All right, but figuring out that reference angle is pretty easy, right? We would just take a full flat rotation or a half rotation around a circle, 180, and we'd subtract 160 degrees and we'd have 20 degrees. We can even have angles that are bigger than 180, and it's important that we're okay with that. For instance, right, if I had my initial ray and maybe an angle that kind of went something like this, so that, oh, I don't know, let's call that a 240 degree rotation, let's say, right? That's okay. I can still think about a reference angle. Okay, I can think about that angle, but again, keeping in mind that since this is 180 degrees, to find that little reference angle in there, I would just do, take my entire angle, 240, subtract my 180, and I'd have a reference angle of 60 degrees. All right? Sometimes the reference angle and the original angle are the same thing. Sometimes you have to do a little bit of geometry. But the reference angle will always be the angle between the terminal ray and the x-axis. Be careful not to do it between the terminal ray and the y-axis, for instance. Right? Let's say that we had this particular angle. Something like this, and I don't know, let's say that that entire thing was 120 degrees. Now again, the reference angle would just be this thing right here. So I'd just, I'd do 180 minus 120, and my reference angle would be 60 degrees. But what some people will do is that they'll draw this in. They'll draw this in and they'll think, oh, there's my reference angle. Now in that case, of course, because we know this is a right angle, you'd have 120 minus 90, and you might think that the reference angle is 30. But it's not. It's not 30. By the way, let me give a nod a little bit to a negative angle. Okay? Let's say that you had your initial ray looking kind of like this, and let's say that you rotate it clockwise now, and maybe we rotate it clockwise, maybe we go, ooh, like this, and I don't know, let's say that that's a negative 150 degree angle. Now really, I just want you to really understand, all that negative really is doing is telling me that I rotated clockwise instead of counterclockwise. This, though, is still my reference angle. All right? And this reference angle is still going to be just 180 minus 150, so that's going to be a 30-degree reference angle. All right? So the reference angle is important, but what's even more important is the idea of sort of putting an angle, you know, in the coordinate plane, in the xy plane, with its vertex right at the origin, letting its initial ray point along the positive x-axis, and then that terminal ray, right, that terminal ray points somewhere else. All right, little review real quick before we move on. Don't forget the quadrant system. Quadrant 1, Quadrant 2, Quadrant 3, Quadrant 4. Many years ago, a student taught me, they said, hey, I remember those by drawing a C. I just draw a C like that. I start the C in the first quadrant, and then the direction that the C goes around, if you sort of draw a C like typical people do, that will show you all the quadrants, okay? All right, I'm going to clear this out, and then we're going to move on. So those are angles. Don't worry yet about radians if you've heard of them. We'll get to those in due time, okay? SOHCAHTOA. Let's remember a little bit of right triangle trig from Algebra 1. You learned all about trigonometry of right triangles in Algebra 1, right? And remember how that worked. If we've got a right triangle, okay, if we've got a right triangle and we've got some angle, we call it A, right? And let's say we had a triangle, the classic 3, 4, 5 right triangle, something like this. Right? Then we define these three trig functions, the sine, the cosine, and the tangent, by using ratios of sides of right triangles. And we define the sine of an angle, so we would say the sine of angle A is the side opposite of angle A divided by the side, sorry about that, divided by the hypotenuse. Okay, so in this case, the sine of angle A would be 3/5. The cosine of angle A, which is the adjacent side, divided by the hypotenuse, is 4/5. And the tangent of angle A, which is opposite divided by adjacent, would be 3/4. All right? So no matter what we do with trigonometry at the Algebra 2 level, we have to make sure that it lines up, that it agrees with this information from Algebra 1. All right? But keep in mind that when we did this in Algebra 1, we only created those ratios for acute angles, for angles that were between 0 and 90. We didn't have negative angles. We didn't have angles that were bigger than 90. We didn't even have angles of 0 and 90, right? I mean, you know, you would deal with these kind of problems where you'd have a right triangle. Remember how this worked. You did a little bit of this in geometry as well, where we might have like a 24-degree angle, then we might have something like a hypotenuse of 8. We might be looking for, let's say, the side length. So we would say, the sine of 24 degrees is the side opposite divided by the hypotenuse. So then I would figure out what that opposite side was by just multiplying both sides by 8. I don't know what that is, but we'd figure it out on our calculator, right? So we have to feel confident with right triangle trig, because what we're going to be doing is extending this so that we can deal with any angles that are acute, obtuse, negative, 0, 90, 180, I don't care, okay? But in order to do that, we have to feel comfortable that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and less important is the tangent, opposite over adjacent. Primarily, let's just concentrate on the SOHCA part of all of this. All right? So just a real brief review of right triangle trig. That's all you're going to get for right now, okay? All right, I'm going to clear all this out, then we're going to go on to the next slide. All right, let's take a look. So now what we want to do is we want to extend the trig functions. And the way that we do this is just absolutely brilliant. We do it by using a circle. So I'm going to switch back to blue for no apparent reason. Let's say that I took a circle. Now, any circle will do, and I really mean that. I know some of you are like, no, all we've been talking about is the unit circle, but let's just not worry about the unit circle. In fact, let's actually take a circle. Let's take a circle that is absolutely beautiful. Let's take a circle whose radius is 5. Now, I do want to center the circle at I do want to have the center of the circle at the center of at the origin, 0, 0. But now let's say that we drew out a ray, right, so that we had some angle here. Let me call it theta. Okay, we often use Greek letters to designate angles, right? And let's say I went through the point 4, 3. Now, the point 4, 3 definitely lies on this circle. This is a circle, remember, that would have an equation x squared plus y squared equals 25, right? Think about that for a minute. All right, you got to make sure you have that, right? Well, this point would definitely lie on that circle. You could tell by like squaring both of the coordinates, etc., etc. 25 equals 25. So yes, that point lies on that circle. Well, we can now draw in a right triangle, right? And the whole point of rectangular coordinates like 4, 3 is that this is now 4, this is now 3, and of course, you know, I mean, if the radius of the circle is 5, the radius of the circle is 5. So now, of course, the cosine of theta, which is adjacent divided by hypotenuse, is 4/5, and the sine of theta is 3/5, right? It's a piece of cake, right? It's really cool. Now, what in the world does this have to do with extending the trig functions? Well, notice what I've got here is I've got an angle that's still acute. But what would happen? What would happen now? Let me clear all this stuff out so I have a new picture to work with. What would happen if I wanted to just extend it? All right, I have the phone ringing. All right, we're back to it. Now, what was the point? The point was we were trying to extend the SOHCAHTOA, or at least the SO and the CA, to all other angles. Well, okay. Now let's go back to having that. Oh my goodness, what just happened? Sorry about that. I gotta activate my pen, otherwise it really just doesn't work well. So let's go back to that circle that's got a radius of 5, right? Now remember, when we had that angle over here, it was easy enough. But now let's put it over here. Now remember, this is x squared plus y squared equals 25, right? So, you know, it's up here 5, down here -5, over here 5, -5. Now, what did we essentially do? Last time what we did is we said, well, the cosine of theta, we took that x-coordinate, right, when we were at the point of 4, 3, we took that x-coordinate and we divided by the radius. We got 4/5, and the sine of that angle, right, that was that y-coordinate divided by the radius. That was 3/5. Well, if we're over here now, let's say that we're now at the point -4, +3. Well, then whatever this angle is, whatever that angle is, I'm now just going to say, well, cosine theta is -4/5, and sine theta is +3/5. So it's really cool. I can extend the trig functions to obtuse angles, angles greater than 90, or even negative angles, or anything like that I want, right? So let's say that I had some kind of angle here. Let me go in red because the diagram's getting a little bit complicated. Let's say I went right here and I kind of knew what the x, y coordinate points were, whatever they would be, right? I can now just say, well, no matter what that angle is, I can say that the cosine of that angle would be the x coordinate divided by the radius, and the sine of the angle will be the y-coordinate divided by the radius. And then everything lines up. Adjacent divided by hypotenuse, opposite divided by hypotenuse, right? So that's it. That's how we extend the trig functions. We simply say that the cosine of the angle is the x-coordinate divided by the radius of the circle. The sine of the angle is the y-coordinate divided by the radius of the circle. Now again, you might kind of say, well, why did a circle suddenly come into play? You know, here we were talking about right triangles, now we have a circle. And the reason is very simple, because any point on a circle really creates a right triangle. You know, there's a right triangle, there's a right triangle, right? Any point on a circle. Here, let's take a look at this one. That right triangle, right? All these right triangles occur because the radius is the hypotenuse, and then the x and the y coordinates are simply the legs. Okay. Let's take a look at a very special circle. Well, okay, not a very special circle. Let's talk about the unit circle and defining sine and cosine. That is a very special circle. Let's first talk about the unit circle. All right, this is the one that you've been using a lot of, and we'll get the really scary looking diagram up. That is a beautiful y-axis right there. The unit circle is the most important of all the circles that we can orient ourselves in trig, and we'll see why in just a moment. The unit circle is by definition a circle that just has a radius of 1, okay? So these 4 primary points on it, right? The point over here at 1, 0, the point up here, right, at 0, 1, the guy over here at -1, 0, this thing right here at 0, -1, right? These 4 points. But what makes the unit circle so great in terms of the sine function and the cosine function, right? Why do we want to use the unit circle? Well, let's draw in one of the most basic triangles, right? Let's put this guy here. Let's put theta here. And let's draw it down like that, okay? Let's take a look at that for a second. Well, because it's the unit circle, its hypotenuse is 1. Now remember, this is just some random xy coordinate point on the circle. Now remember, the equation of the unit circle, unlike the one that we were just looking at, is x squared plus y squared equals 1 squared. So that's the equation of this circle, right? And that's actually very, very important. So, you know, I've got this triangle. This is x and this is y, right? So I've got this little right triangle. Let me pop it out like that, right? Hypotenuse is 1. This is x. This is y. Well, remember, we said that the cosine of the angle was going to be x divided by r, but in this case, r is 1. So the cosine of the angle is just that x coordinate. And the sine of the angle, right, let me just go through it all because I got to get through it. Well, the sine of the angle is the y coordinate. And this is awesome because it gives us a way, this one simple tool, the unit circle, gives us a way of thinking about what the sine and the cosine of any angle are. Think, it could be positive rotation, it could be a negative rotation, it could be more than 360, less than 180, it could be acute, obtuse, it doesn't matter. And all we have to do is orient the angle right. And if we want to know what the cosine of the angle is, we simply take the x-coordinate. If we want to know what the sine of the angle is, we simply take the y-coordinate. So let me give you an example of this, right? I'm going to clear this out, okay? You'll often get a problem that is pretty easy. It'll say something like, say the point 5, 13, let's see, what would it be? Let's say -12, 13 lies on x squared plus y squared equals 1. By the way, it does lie on that, right? And then maybe I say, hey, well, what's the value of cosine theta? Well, on the unit circle, cosine theta is x, so the cosine of theta will just be 5/13. The sine of theta, well, that's just y on the unit circle, so that would be -12/13. So it's really simple. As long as I know that a point lies on the unit circle, radius of 1, okay, r equals 1, then the cosine of the angle is just going to be the x-coordinate. The sine of the angle is the y. I know that those fractions are obnoxious. It's just kind of the way it is. I'm sorry about that. But think about it, right? That point's got a positive x-coordinate and a negative y-coordinate, so it's probably something like that, right? I don't even know what the angle is, but the idea is, and I'm sorry I missed the point. Let's make the point really big, like that, right? The idea is whatever this angle is, remember it's always being measured from the positive x-axis. Whatever that angle is, theta, I can say the cosine of theta is 5/13 and the sine of theta is -12/13. That's it. Now watch out. Sometimes you'll get problems. I'm going to clear this out. Sometimes you'll get problems where they'll just say something like, you know, the terminal ray passes through, let's say the point, let's say 6, -2. What's the sine of theta? All right, well, this isn't on the unit circle. Isn't on unit circle. It's not. It's on some circle, but it's not on the unit circle, right? So let me draw a picture really quick. Okay, I got some circle. Right, what would that point look like? It'd be like 6, -2, maybe it's like this. I don't know. That seems a bit right. That bit right. Well, look, at the end of the day, the sine of the angle is y divided by r. That's what it is. Okay, only on the unit circle where r is 1, right, on the unit circle can I say sine is y. But what I need to do, I know y is -2, that's good, but I would need to find the radius, and that would be easy, right? What would it be? It would be, I'd get 6 here, I'd get 2 there. I'd do a little bit of Pythagorean theorem. I'd say, 6 squared, come on. 6 squared plus 2 squared is equal to c squared. Apparently I can't do the Pythagorean theorem. 36 plus 4 is c squared. C squared is 40, so c would be root 40. If you felt the need, you could simplify the radical. It's 2 radical 10, whatever. But the sine of theta at the end of the day would be the y-coordinate, -2, divided by the radius, square root of 40. And again, you know, if you have to simplify, you could simplify. You know, you could cancel those 2's. -1 divided by root 10. If you felt the need to get rid of that square root in the denominator, eventually, wow, that would be our final answer. But that's not really the point. We're not getting so deep into that. Ultimately, the unit circle, though, is our best friend. The unit circle is absolutely positively our best friend, because if I want to know the measure of the cosine or the sine, I just take the x-coordinate on the unit circle. That's my cosine. I take the y-coordinate on the unit circle. That's my sine. All right? I'm going to clear all this out, and then we'll keep going. Radians versus degrees. Okay, you had to know this was coming. All right. Now, for a very, very long time, you only measured angles in degrees. And then all of a sudden, radians came along. Radians are defined by one primary geometric idea, and I'm not going to develop them really heavily, but it's this. If I have part of a circle, so I've got some part of a circle, right? So I got a radius, and that radius sweeps through an arc length, so an actual length, arc length, all right? Then we will define the radian angle that the radius passes through, or that the arc passes through, by a simple formula. Theta equals s divided by r. So when we measure angles in radians, what we're really just measuring is the ratio of the arc length to the radius. Boy, isn't that helpful. Well, maybe not so much. That formula is important, and it gets used for all sorts of knick-knack problems. For example, something simple. Sorry, I got some problems sitting down here, but I didn't move them over here. You know, for instance, you know, you might get a problem that says something like, we have a central angle that intercepts an arc of length, let's say 24 inches. If the radius is 4 inches, what is the radian angle? Right? Well, it's simple. The radian angle will always be the arc length divided by the radius. In this case, the arc length is 24. The radius is 4, so the radian angle is 6. Now you might look at that and go, wait a second. I'm pretty sure all radian angles have a pi attached to them. So let's delve into that. Why does pi show up so much when you talk about radian angles? All right. So I'm going to clear this out in a moment. Okay. But we're going to see why pi comes up a lot. So keep in mind that the definition of radians is arc length divided by radius. Well, let's just say for a minute you had your radius and you went all the way around, right? A 360-degree rotation. Well, what is that in terms of radians, right? What is that in terms of radians? Well, if you go all the way around, you're going the entire circumference, the circumference of the circle, right? Well, what is the circumference? Well, you know, the circumference is pi times the diameter of the circle. That's not very helpful. How about pi times twice the radius of the circle? Well, in that case, what happens is that the radii cancel, and a full rotation is 2 pi radians. That's just the deal. So when you go all the way around, one full rotation is 360 degrees, or 2 times pi radians. Now keep in mind that's a number right around 6, right? It's about 6 radians, right? And the reason for that is that pi is just about 3, right? 3.14, so that's about 6 radians, okay, in a full rotation. Okay, radians actually quite a bit. It's about 60 degrees of rotation, all right? So there's just, 2 pi radians. It would have been so nice if it had been just pi radians in a full rotation, but it's not. Now, one thing that you can immediately do is you can say, well, if 2 pi is a full rotation, right, which is equal to 360 degrees, then pi must be a half rotation, and that must be 180 degrees. Likewise, you can then say that pi divided by 2 would be a quarter of a full rotation, and that would be 90 degrees. And these are very important to know, very important to know. A full rotation is 2 pi radians, a half rotation is 180 degrees, and a quarter of a rotation, a 90-degree angle, that's the same as pi over 2. Now, that being said, let's like hone in on this one just for a second, because often this one is used to convert back and forth between radians and degrees. For instance, I'm going to clear this out, okay? Let's just, let me get this, pi radians equals 180 degrees. Let's say I asked you to convert 32 degrees into radians. This is just simply what I would call a unit conversion problem. Well, I would do 32 degrees, and I'd multiply by pi radians divided by 180 degrees. Now, why do I do that? Well, number one, because these two things are equal. All right, so really that fraction's equal to 1. But why do I have the pi radians in the top and the 180 degrees in the bottom? I do that in order for myself to be able to cancel. I'm looking for my calculator now. Hello. To have the degrees cancel and be left with units of radians. We'll go the other way around in a second. But then you just literally use your calculator, 32 times pi divided by 180, and we get a very unsatisfying 0.55, let's say 8 radians. All right, so 32 degrees and 0.558 radians are the same. Now sometimes radian angles have a pi left in them. So let's say we were asked to convert pi over 3 radians into degrees. Pi over 3 is a very important one. Well, I might just go, let's see, I've got pi over 3 radians times, this time I'm going to leave the degrees in the top because that's what I want to be left with, and I'll put my pi radians in the denominator. Now the radians cancel, but so do the pi's, and now I just have 180 divided by 3, and I find 60 degrees. Pi divided by 3 radians is 60 degrees. In fact, there are some very, very important ones, right? We already listed the fact that 2 pi radians was 360 degrees, that pi radians was 180 degrees, that pi over 2 radians was 90 degrees, but we can add some other ones on that are very important. Pi divided by 3, well, that's 60 degrees. Pi divided by 6, we could do the same thing and we'd find out that's 30 degrees. One last one that's important. And pi divided by 4, well, that's 45 degrees. These are all very important ones. It's helpful, probably not mandatory, but pretty helpful to have those memorized. All right? So we'll be working in radians and we'll be working in degrees for the rest of the trig unit. I'm going to clear this out for right now. Lots of time. Not lots of time left in the period, but lots of time left to record the video. All right, the special angles and values. The special angles and values. I've got a random sheet that's blank. Now let's take a look at them. Okay, remember how I was just talking about like the 30, the 45, the 60, pi over 6, pi over 4, pi over 3? Well, at these values, okay, we can determine, notice we're on the unit circle, we can determine exact coordinate pairs, and they are weird looking. So at 30 degrees, we've got root 3 over 2, 1/2. At 45 degrees, we have root 2 over 2, root 2 over 2. Notice at 60, we have the same pair as at 30, but they're flip-flopped, right? They've gotten flip-flopped, right? Now, why are these things important? Well, that's actually pretty debatable in my mind, but they're important because what we can now do, right, remember, the cosine of the angle is equal to x, and the sine of the angle is equal to y. Well, I could now say, let's say I took 30 degrees. I could say, well, the sine of 30 degrees, that's 1/2. And if you took your calculator out right now and you had it in degree mode, watch your mode, and you said, hey, what's sine of 30? It would tell you 0.5. Right? But we can extend it, right? We can use the x and the y definitions of sine and cosine all over the place. So for instance, let's go cosine. If I wanted the cosine of 135 degrees, I could just go, oh, okay, here's 135. Cosine is the x-coordinate. That's negative root 2 over 2. By the way, that's about negative 0.707 if you want to check it on your calculator. All right? Now, this is gosh, is this a scary circle to look at. And in fact, the New York State Regents expects you to be able to deal with any of the angles that you currently see on this picture in both radians and degrees and know all those points. You might look at that and go, wow, is that overwhelming? Wow, is that overwhelming? But here's the thing. You really only need to memorize the first quadrant and then know the basic things at these points. Okay, the basic values at the quadrantal angles, 90, 180, 270, 360, or pi over 2, pi, 3 pi over 2, that's 270 degrees, that's an important one, and 2 pi. All right, here's why you only need to know the first quadrant. Okay, pretend you can't see any other quadrant. Seriously, I know, but pretend. Okay, let's say that I wanted to know what the cosine of 150 degrees was. All right. Well, what I would do is I'd look for the reference angle. Do you guys remember the reference angle from a few minutes ago? So I'd say, all right, let's see, 150 degrees would look something like this. Its reference angle would be 30 degrees. Now, take a look on the diagram really quick. Here's my 30-degree pair. Here's my 150-degree pair. Do you notice something about them? They're exactly the same, except the x-coordinate's negative, but the y-coordinates are the same. It's this beautiful symmetry of the circle. So the thing that's important about reference angles is that reference angles and the angles that they come from will have the same sine and cosine. They'll just be different by a plus and a minus, right? So in other words, I know that the cosine of 150 and the cosine of 30 are, are more or less the same, but there may be a plus, there may be a minus. I got to think about that. So how do I figure it out? Well, I know that cosine of an angle is the x-coordinate, and in the second quadrant, the x-coordinate is negative. So I know that the cosine of 150 degrees must be a negative. Since I know the cosine of 30 is root 3 over 2, the cosine of 150 must be negative root 3 over 2. All right? And you can do that for all sorts of angles. Like let's say you were looking for the sine of 315 degrees and you didn't have the whole diagram. You only had memorized the first quadrant. Well, you could say 315. Well, 315 is in the fourth quadrant. Okay, it's bigger than 270. It's less than 360. I apologize for the noise. So it's going to look something like this. Right, this is my 315 degrees. Here's my reference angle. That's my ref. What is it? Well, I'd do a little 360 minus 315, and I'd find my reference angle is 45. Then I'd say to myself, well, sine of the angle is the y-coordinate, and in the fourth quadrant, that y-coordinate is negative. So the sine of 315 must be the negative sine of 45. And then if I know the sine of 45, right, root 2 over 2, then I would know that the sine of 315 is negative root 2 over 2. And that's it. That's the whole deal, right? That's why reference angles are so very critical. Not just for these angles, but for any angles, right? So that if for some reason I knew what the sine of 70 was, then I could find out the sine of any other angle that had 70 as a reference. All right, well, this picture is getting crazy. So what I'm going to do is I'm going to clear this out, and then we're going to keep going. Oops, stray mark. All right, well, the last thing that we're really going to look at today are the other 4 trig functions. You see, we had sine, we had cosine, but there's actually 4 other trig functions. There's the tangent function, there's the cotangent function, the secant function, and the cosecant function. Now the key is, each one of these other ratio functions is simply defined in terms of sine and cosine. And these are 4 formulas that the Regents expects you to memorize. Although you'll get a formula sheet at the end of the year, these 4 won't be on it. So tangent is sine divided by cosine. Cotangent is cosine divided by sine. Secant, oh, isn't this terrible? Secant is 1 divided by cosine. Why couldn't it have been 1 divided by sine? Ugh. And cosecant is the 1 divided by sine. That's obnoxious, obnoxious, obnoxious. But what are you going to do, right? So, well, great. We've got all of these. What in the world do we do with them, right? What do we do with them? Well, you know, one thing that we could ask ourselves is just how do we evaluate them? So, for instance, let's say I wanted to know what the tangent of 60 degrees was. Well, the tangent of 60 degrees is going to be the sine of 60 degrees divided by the cosine of 60 degrees. That's just the formula, right? Now 60 is one of those special angles. So if you need to, look back at that unit circle diagram, right? The one that was on the previous sheet. All right. The plain fact is, if I look at it, the sine of 60 degrees, which is the y coordinate, the cosine of 60 degrees, which is the x coordinate. Sorry about the bell there. We're going to get another one in just a bit. The sine of 60 degrees, well, that's root 3 divided by 2. The cosine of 60 degrees, that's 1/2. I don't want to leave this complex fraction, so maybe I would multiply both top and bottom by 2. And I would find that the tangent of 60 degrees is root 3. So that's one thing that I can do, right? I can now take those definitions, and I can use them to figure out the tangent, the cotangent, the secant, the cosecant at a variety of different angles. For instance, let's say that I wanted to know what the secant of, let's go 60 degrees. Well, the secant of 60 degrees would be 1 divided by the cosine of 60 degrees. But I could look at that unit circle, and I would see that the cosine of 60 degrees was 1/2. So I'll multiply top and bottom again by 2, and I'll find that the secant of 60 degrees is 2. So the most basic thing that you've got to be able to do with the tangent, the cotangent, the secant, and the cosecant is to be able to do that. Now watch out. I know some of you are saying, man, I got my calculator. My calculator's got sine, cosine, and tangent on it. I don't need to know these. But your calculator doesn't have secant, cosecant, and cotangent on it. So if you were asked what the secant of 60 degrees is, you got to at least know it's 1 divided by cosine. If you don't know that, you can't even punch the buttons on your calculator. So as much as I hate to memorize things, you've got to memorize these 4 formulas. You absolutely, excuse me, positively have to. Now, one thing that we haven't talked much about is just what the sign of these functions are in various quadrants. And by sign, I mean, are they positive or are they negative? For instance, let's say we're in quadrant 3, right? Let's ask this question. Is cotangent of an angle positive or negative in the 3rd quadrant? Well, let's think about this for a second. The cotangent of an angle is going to be the cosine of the angle divided by the sine of the angle. Now, I just want to think about that in terms of the unit circle. The cosine of the angle is the x-coordinate on the unit circle, and the sine of the angle is the y-coordinate. Let's think about quadrant 3. Right? If we had this unit circle and we had a point, let me draw in red, a point in the third quadrant, well, the x-coordinate would be negative, right? The y-coordinate would be negative, so the cotangent would be positive. The cotangent would be positive in the third quadrant. That's it. Let's do another one. I gotta clear out the screen. Let's say I wanted to know, let me go back to blue, is secant theta positive or negative in quadrant 4? By the way, everything's positive in quadrant 1. We love quadrant 1. Quadrant 1's our favorite. Everything's positive there. Anyway, let's take a look at secant. Secant theta in quadrant 4. Well, secant theta is 1 divided by cosine theta. Again, let's take a look at that. Let's say that we're on the unit circle. All right, we don't have to be on the unit circle. We could be on any circle, and we're still going to work, right? It's still going to work. Let's say we're down here in quadrant 4, and we've got some point, right? So this is our angle. That's our theta. Well, what do we know? I mean, 1 is just 1, but cosine is the x-coordinate. And in the fourth quadrant, the x-coordinate is positive. So I've got a positive, I've got a positive, that must be positive. In fact, secant will be positive whenever cosine is positive. Cosecant will be positive whenever sine is positive. That 1 makes no difference. Tangent and cotangent are trickier because they involve both the sine function and the cosine function. And that can make life a little bit tricky, all right? One thing that you're often asked to do with all of these functions is do some manipulation with them. For instance, let's say somebody asked us to express 3 times the tangent of theta times the cosine squared theta in simplest terms. Right, express this in simplest terms. Sorry about how messy that is. Well, a couple different things. First off, right, I would replace the tan theta with sine theta divided by cosine theta. Now, what in the world does this mean, right? Does that really mean I'm going to take the word cosine and multiply it by itself? Nah. I'm sorry about how messy that looks. Let me write it a little bit neater. Cosine squared theta just literally means cosine theta times cosine theta. So I'm going to write that down, cosine theta times cosine theta. So now I could actually cancel those two, and I would simply get 3 times the sine of theta times the cosine of theta. And that's as simple as it gets. There's just absolutely nothing else I can really do with that. But that's one of the different types of manipulations you can be asked to do with these other 4 trig functions. Just some basic rational algebra. I say it's basic, but it's typically like, oh, I write this fraction, and I have to cross cancel or something along that effect, just like what we had. Right? Let me see if there's really anything else that we haven't covered. Ah, yeah, one last thing. Okay? These 4 functions all have division going on. I'm dividing by cosine, I'm dividing by sine, dividing by cosine, dividing by sine. Right, remember, we cannot divide by 0. We cannot divide by 0. And yet, the cosine function can certainly be 0, and the sine function can certainly be 0. So sometimes you're asked, let's answer this question. What angles make tangent of theta undefined? Okay, let's try to answer that question. What angles make tan theta undefined? Well, the tangent of theta will be sine of theta divided by cosine of theta. Now, the only way tan theta is going to be undefined is if cosine theta is equal to 0. But what angles make cosine theta equal to 0? Well, let's go back to the unit circle. We always go back to our friend the unit circle, right? Now, let's just look at something for a second. This is the point 1, 0. This is the point 0, 1. This is the point -1, 0. And this is the point, This is the point 0, negative 1. Now remember, the cosine is the x-coordinate. So to make tangent undefined, I need every angle that ends up in a place where the x-coordinate is 0. That's up here, and it's down here. So what angle is up there? Well, one angle is 90 degrees. What angle is down there? Well, that would be 270 degrees. So tangent will be undefined when theta is 90 degrees and when theta is 270 degrees, right? So that's about it. All right, I'm going to get rid of all this stuff for right now. That should be enough to get you on your way in terms of the trig. All right, I hope that this has been helpful. I wanted to give you some background. Where did the trig come from? How are radians involved? What should you be able to do with them? What functions are there other than simply sine and cosine, right? And then what might we ask you to do with those other functions, at least for right now? All right. Well, I hope this video has helped you solidify your trig knowledge a little bit. I wish you the best of luck with your studies. Until next time, my name is Mr. Weiler, and this has been Algebra 2 with Trigonometry.